It's a good idea at this stage that we revisit De Morgan's theorems because that can help us defining our functions where we can write a given realization of a logic in one or the other way, either as a pull down network or a pull up network. So let's take a look at some of those because these are helpful. A and B complement is equal to A complement or B complement. So if we draw a truth table, we can easily see these properties between two inputs, and these are extendable to any number of inputs or equations. So we'll try not to go into too detail because that's a complete subject in its own. But let's see how do these values look like if we are to see the actual application of uh, this first theorem of De Morgan. So we take the values, two combinations of all these values. So we see that for AND operation, at least uh, any zero will result into a zero output. And if I take complement, that's just straightforward. I took the complement of that. And now we can take complement of the inputs and then see the right hand side. And we can see this is as long as one of those is high, we'll get high. This is the OR operation. And if you compare this with this, we get the same result. So this is what you can uh, see when we make a circuit. So we can see this can be transferred from one type of relationship to another relationship easily. So this is where complements can be converted into each other. Another theorem is the distribution of complements. So if you have an OR complement, this can be written as the complement of individual inputs with an AND between them. So again, for this also we can write a truth table and see how would that hold. So again, A, B, now we take A plus B and we take its complement, which will be left hand side, and then we'll see how would that hold for the right hand side. So again, start with the inputs. Here it's an OR, so at least one of those inputs can turn high input can turn the output to high. So now we take the reverse, the complement, and we can see straight away that the output will be high only when all inputs in an AND operation will be high. So here again we can see that both are same. That's the second theorem. Now there are associative properties as well, which help us break down some relationships when if you go from one type to the other type, and that those can be written as commutative as you can just switch and it doesn't make any difference. Distributive law is, so if you have an AND with if you have an OR with AND, that can be distributed as A plus B and A plus C. So you can make two ORs and you can AND them. In a similar way, if you have, so this was, in a similar way, if I have an input which is AND with an OR of 2, that can be again written as AND of 2 inputs plus, which depicts OR of, so A is then applying with on both of those, so that's distributive law. And if you add a 0 that doesn't have any, if you or a 0 that doesn't have any effect. But if you have an input and you do the AND operation, you get the input back. So that's the identity laws. And the complement laws are that if you AND two of those, you do OR the input and its complement, you get high, because in either case one of those will be high. But if you do the AND relationship, then of course, but all of them have to be high, so what you'll get would be a low. So this is Boolean algebra, De Morgan's law and Boolean algebra. They both are important for us to go from one type of network to other type of network, and that helps in creating complex logic or complex combination of pull-up networks and pull-down networks. So we can make complex gates equipped with these De Morgan laws and Boolean algebra rules. We can easily change from one type to the other type. So let's look at a complex logic function, which is y equals a and b or c d, the complement of that. Now this can be written as the complement of y as well, so which is the just looking at, so if this is what you gives a high, then the complement would also hold, so it will go the other way as well. So now, like we have done before, we can look at this either way, but if y is low, then we have to see that how this can be high, the result of this can be high. So this just helps a little bit better than solving that one. So here what we see that y should be low for, what are the conditions for a has to be high and this whole thing has to be high, right? So let me put this blue and this green. So this green and blue parts, they both have to be high. And in the blue part, then we have to have simultaneously either B is high or C and D both are high. This or gives us that this part, which I can say with yellow, or this part, which I can pick up as another color. This has to be high. So how do we break it down? So we can easily get pull down network from this because the output has to be 0. So for pull down, you have to have straight NMOS on the in the circuit, and we can make it more simplified even than that. And for that, we will have to apply De Morgan's theorems on this. And let's take a stab at that how we can simplify the right hand side to get an easy handle on how we would make our circuit. So the complement can be applied by changing it from AND to OR, where the complement applies on the changes OR to AND. So sorry, AND to OR, and the complement gets applied to those subparts in there. And then this can be further simplified by A complement plus B complement and CD complement. So it's more like divide and rule, and we can write it then as C complement plus D complement. So going back to this De Morgan's rules that we just studied, we can apply these to simplify our situation, to divide and conquer. Now, this is now telling us exactly what each input has to go through and how those inputs have to be connected to each other. Now, in this case, we are going to use a pull-up network because to have the output low, the whole thing has to be high, which means, so all these individuals have to use a pull-up network for our output to be high. Now, in this case, we can see that to get Y as high, we need to have A, complement of A, or this part to be high. And in this part, then we can further see that this is where, so both of those then result into something that can give us the Y value as low or high. Either one of them can do that. So we can see that in case of pull-up network, then we can use the parallel network and then further break down the right hand side too, as we have done before. So the circuit for these two applications can be written either as a pull-up network or pull-down network. So let's see, if we do pull-up network, how would that be? So let me write down the logic that needs to be implemented, which is Y equals A, B plus C, D complement. So we can straight away have a parallel network where we can straight away put A to come together on the other branch So this is AND between these two. Now, that would be a little bit more complicated. First, we got B, and then it can be OR, so either of those. So which means we would branch it, and this would be A, this is B, and C, but this is, we are putting it as all pull-up networks, PMOS. They come together, so these are in parallel to A prime. So this is C and this is D. So that would be how a pull-up network would give us output Y, but in CMOS you can also implement the pull-down network using NMOS. So now those were here. So this equation needs to be implemented there, where, let me just write it there. So all right, so A is now in series. They both have to be active, but there are then two branches. I can give input C here, and in series would be D, and this would be B. So this is how we can implement the logic, either using pull-up network or pull-down network, either using PMOS or NMOS. Now, looking at these, we can also convert a PDN into PUN, because we can see that when there is a series branch in one, and it's implemented as a parallel branch in the other one. So, which means we can obtain one from the other type. So here we can see that if this part C and D were in series, so here they were in parallel. So same B was in parallel with these in this guy, but this was in series with these guys. So hence there is a direct translation that's possible. For simpler circuit, it's a straightaway process, but it may be a little bit more complicated for if we have more complex networks. But for the most part, for this course, we can see simple translations where one can be obtained from the other, and we just have to express the Boolean expression in terms of the other function. So like we just saw that we could get PDN by applying Boolean expressions using De Morgan theorems, we could convert one type to the other. So we have to manipulate the Boolean expression to basically convert one type of network into another type of network. So this is, we can think of, there is duality to the process where we can obtain P1 from PDN. We can get pull-up network from a pull-down network. So let's see an example. So it's XOR exclusive OR function, which is written as AB prime plus A prime B. So exclusive OR is, we can see that we are given Y instead of Y complement. So we can create pull-up network easily. So we have to have high at the output. So, but Y is not a function of the only the complement variables like we had before. It's now combination of complement and non-complement functions. So we need to have then additional inverters at the input of B and at the input of A when we are hooking it up to the other side. So from this we can straight away just write down with PMOS, we can write a function where we show the input to be complemented. So we write A prime, which means there is an inverter that's being used. So now these come in series, and this guy comes in parallel with the whole thing. So we can write down A here, sorry, this was B, in parallel with B prime. So that's how we can implement it in terms of additional inverters here. So this extra inverter is just a simple circuit that would change the input. But now we could also play with the Boolean algebra, and we can get Y complement equal to AB plus A complement B complement. So this is then the pull down network version of XOR, but now we can see that we are presenting it in terms of Y complement. So this is where we have to then make a similar relationship of transistors to get the required output. And that can be in a CMOS, then that can be made to express the network in addition to PMOS. So there is this method now which we have gone through. So the idea is that there are few steps involved on what we do and how do we approach it. We can create pull down network if we can express our output in terms of its complement. So we can just express this in terms of uncomplemented inputs, which is slightly straightforward. Now, if there are complemented inputs are there, so we just add an inverter to express them. So if we do the simple uncomplemented inputs, the complement would be where we would have to just put an inverter there. And if you want to make a pull up network, so this is for pull down for NMOS, our output is going to 0. In case of pull up PMOS, that can be expressed in terms of the y as a function of the complemented variables. So then our inputs are opposite to what we are getting at the output. So we then apply uncomplemented variables to the gate of PMOS. So again, if we come across uncomplemented inputs, we use inverter, and we can go from pull-up network to a pull-down network both ways by using the duality property and the De Morgan's rule. So these are the basic approach of dealing with a difficult or apparently complex circuit or complex situation, but we can see that there is always the conversion which may be much easier than from a pull up to pull down may be easier to do than the other way. So that's where we can break it down to smaller pieces and work with it. So now there is example that